So, you're building an aircraft and need to build some wings. Today I will be covering how to use the wing editor and aerodynamic properties of airfoils and wings while comparing Flyout's current implementation of them to real-life approximations. The overall wing tutorial will be made up of multiple videos, and this one in particular is focused on properties of wings at speeds below Mach 0.3, otherwise known as incompressible speeds. Although this may not sound like a particularly exciting flight regime, it is an important one to be familiar with due to the fundamental nature of aerodynamics at these speeds. Much of the information presented in this video will be taken from a set of references that will be listed in the description and throughout the video. As usual, the video will be broken up into chapters with timestamps shown on screen now. Upon placing a wing part and opening the wing editor by either pressing Tab or the Open Wing Editor button, we are presented with a set of 4 nodes which can be moved around to adjust the wing shape. Adjusting the green scaling vector will change the thickness of the selected nodes. To select multiple nodes at once, hold Shift while clicking them. By default, the leading and trailing edges of the wing are completely flat, which will cause the wing to have poor aerodynamic performance. As such, it is generally necessary to give your wing leading and trailing edge parts, which can be done with the drop-down lists in the pane on the right with the wing selected. Currently, we only have one option for each of these, but hopefully we will see more additions in the future, such as Fowler flaps or leading edge slats. In addition to improving the performance of the wing, the leading and trailing edges can be assigned inputs to act as control surfaces. Reopening the wing editor, we can see that there are now 4 additional nodes assigned to the leading and trailing edge parts. Changing the distance between the main wing nodes and the leading and trailing edge nodes will change the size and bluntness of the leading and trailing edges. The effects of this will be discussed later. If you need your wing to have a more complex shape, or need to change how much of the wingspan your control surfaces take up, you can split the wing with the split tool at the bottom center of the screen in the wing editor. Doing this will split the wing into multiple sections adjacent to the spanwise location that it was split at, and new nodes will be added along the split line. There's no limit to the number of times you can split a wing. When splitting a wing section, be aware that any settings the control surfaces had will be deleted, as the game is deleting the original parts and replacing them with 2 new sets of parts that match the shape of the original wing section. With this in mind, make sure you have finished splitting your wings before you start configuring control surfaces or painting the wing. Note that simply placing a new wing part on an existing wing part does not add to the wing the same way the split tool does. This throws off certain calculations involving wingspan and wing area that will be discussed later in a way that can significantly impact wing behavior, as both wing parts will behave separately. You can sweep the wings by moving a set of nodes in the longitudinal direction of the aircraft. It is generally good practice to create sweep using this method rather than moving individual nodes within a set along the lateral direction of the aircraft. Additionally, you can use the offset tool to move a wing section around without the rest of the wing adjusting its shape to match the new location of the nodes. Keep in mind that as you adjust the location of one of the nodes at the discontinuous section, the wing shape will readjust to match the location of the new nodes. This can be used to create a dogtooth, which will be explained later on. Looking further down in the wing settings, we have wing strength, which, as the name suggests, affects how strong the wing is when the soft joint option is enabled, which allows the wing to flex and even break off if it experiences too much loading in flight. This setting also affects the mass of the wing part, where a higher strength wing will have a higher mass than a lower strength wing. If you need your wing to handle higher g-forces than it can currently take even at maximum strength, you will need to increase the size of the node line that is braking. The easiest way to do this is by increasing the thickness of the nodes, but this will cause more drag, which will be explained later. Next, we have the root and tip twist. These will affect how much incidence the root or tip of the selected section will have, and the wing section profile will be twisted gradually between its root and tip. The purpose of this will be discussed later. Moving on, we have the pushrod settings. The pushrod is purely cosmetic and can be used to add some extra detail to your plane. The drop-down allows you to select what side of the wing the pushrod appears on, and can be set to none if you do not want one. The spanwise location of the pushrod on the wing section can also be adjusted with the slider. As mentioned earlier, we have the soft joint option. Checking this reveals a slider that allows the stiffness of the wing to be adjusted, where a stiffer wing will flex less under loading. When using soft joints, make sure the section of the wing with the option enabled is not very thin, otherwise it will flex a lot more than may be desirable. Also be sure to avoid using soft joints on wings that are attached to control surface motors for the same reason. There is also a bug that can occur with soft joints where the apparent mass of the plane increases significantly for some reason, despite not being indicated in the editor. Keep this in mind if you choose to use them. We can also add a fuel tank to the interior of the wing section and choose its fill percentage. The amount of fuel the tank can store depends on the size of the wing section, not counting the leading and trailing edges. We can also adjust the fuel priority slider, where a higher number will drain first. Finally, we have the wing's information window. This is accessed by right-clicking a wing in flight. Note that this information is not currently visible if the wing section you click on has a fuel tank. From top to bottom, we have the wing section's angle of attack, followed by the lift coefficient display. The lift coefficient display also shows the maximum lift coefficient it has reached in flight and the angle of attack it was at when this occurred. Note that the lift coefficient displayed only accounts for the central wing part and not the leading or trailing edges. The angle of attack, however, does account for these. Next we have the drag coefficient, which also shows the percentage of drag that is induced versus parasitic. These will be explained later. Moving on, we have the lift to drag ratio, a percentage of how stalled the wing section is, and the wing's effective aspect ratio. This last element accounts for the entire wing, including mirrored parts. Before I cover how different wing setups affect performance, I will need to cover the basics of how airfoils work. Before I do, however, I feel it is important to state ahead of time that the way wings and airfoils are modeled in the game are not perfect imitations of reality due to the complex nature of aerodynamics. Even so, there are some things that are either modeled incorrectly or are not modeled at all that should and could be, which I hope to see in the game's future. Some of these aspects of wings and airfoils may not be widely known, so please do not give the developer a hard time over them. With that in mind, let's get into the basics of airfoils. An airfoil is simply the two-dimensional cross-section of a wing and has a few defining characteristics that we will need to familiarize ourselves with. First, we have the chord, which defines the length of the airfoil from the tip of the leading edge to the tip of the trailing edge and is denoted by the letter C. The line between the leading and trailing edge of the airfoil is the chord line. Second, we have the thickness, denoted by the letter T. This is sometimes defined as a fraction of the chord, in which case it becomes the thickness to chord ratio, T over C. This measures the maximum thickness of the airfoil. The next defining characteristic is the camber and the mean camber line. The camber line is defined by points halfway between the upper and lower surface of the airfoil, and the overall camber of the airfoil is the maximum distance between the mean camber line and the chord line. If the airfoil is symmetrical, the mean camber line will be aligned with the chord line, and the airfoil has zero camber. In Flyout, the airfoil shape of the wing part is symmetrical by default, but with the use of a default value and an input on the leading or trailing edge, we can mimic the behavior of a cambered airfoil. According to thin airfoil theory, the lift coefficient produced by any thin airfoil can be calculated by multiplying the angle of attack, denoted by the symbol alpha, by 2 pi, where the angle of attack is the angle between the airfoil's chord line and the direction of the incoming air. It should be noted that the angle of attack used in this equation is in radians, so if we want the lift coefficient per a given angle in degrees, we must multiply the previous equation by pi over 180. This relation tells us that an airfoil's lift generated increases linearly with the angle of attack. In Flyout, one can approximate a generic airfoil's performance using a rectangular wing with a very high aspect ratio, a term which will be explained later. The Observing the lift coefficient's values as the angle of attack changes, we can see that the lift curve slope conforms reasonably accurately to that of thin airfoil theory, but only for the main wing part's readout. Using the flight window, we can see that taking the leading and trailing edges into account, the lift curve slope is actually steeper than it should be. Because this expression obtained only gives us the lift coefficient, we still don't have the actual lift generated. To obtain the amount of lift the airfoil generates, we must multiply this coefficient by the dynamic pressure and the airfoil's chord length. The dynamic pressure is a metric obtained by multiplying the product of the free stream velocity squared and the free stream air density by 1/2. Multiplying the lift coefficient by the dynamic pressure and airfoil chord will give us the lift force generated per unit span of the wing that the airfoil is a part of. If we want the full lift generated by said wing, one might assume we just need to multiply the lift coefficient and dynamic pressure by the wing area instead of the airfoil's chord length, but going from a 2D airfoil to a 3D wing makes things less straightforward than this, as will be discussed later on. Next, I will discuss the effects of camber, but first I will give a very simplified explanation of the physics behind lift generation, starting with the symmetrical airfoil at zero angle of attack. As the air is influenced by the airfoil, the local velocity and pressure of the air change at different locations on the airfoil. Areas with the highest velocity will have the lowest pressure, and vice versa. As the pressure acts on a part of the surface will experience a force per unit span perpendicular to itself. If we take the components of this force that are vertical relative to the chord line and add them all up for every point along the surface, then we can get the normal force that the airfoil experiences. Doing the same for the force components that are parallel to the chord line will give us the axial force that the airfoil experiences. When the symmetrical airfoil's angle of attack is 0, the airflow over the upper and lower surfaces are symmetrical. Because of this, the pressure distribution is identical on the upper and lower surfaces, and the normal forces that each surface generates cancel each other out, generating 0 normal force. If we raise the angle of attack, the flow field along the upper surface and lower surface become different. The air above the upper surface is overall moving faster and has a lower pressure than the air below the lower surface. Because there is now a difference in pressure experienced by both surfaces, the normal force that the airfoil experiences is no longer 0. It should be noted that this normal force is not equal to lift, nor is the axial force equal to drag. The reason for this is that lift and drag are both specifically perpendicular and parallel to the direction of the incoming air, respectively. To transform the normal and axial forces into lift and drag, we can do a simple rotational transformation involving the angle of attack. I should also mention that this pressure difference between the upper and lower surfaces is not the only mechanism that generates lift, with the other being the downwards turning of the airflow by the airfoil, imparting a downwards mass flow component that gives rise to an upwards force due to Newton's third law. It is important to know that both the pressure and momentum aspects are required for lift to be generated, as both sustain each other. There are several misconceptions regarding this, two of which are that the pressure and momentum contributions are independent of each other, or that only one of these mechanisms is required to fully generate lift. If you are interested in learning more about this interaction between the pressure field and the direction of the flow contributing to lift, I would strongly suggest reading the book that I have listed in the references by Doug McLean, a former technical fellow at Boeing. Now let's look at the cambered airfoil at zero angle of attack. Because the upper and lower surfaces are asymmetrical, the velocities and pressures experienced by the upper and lower surfaces will be different, with the upper surface experiencing an overall lower pressure and the lower surface experiencing an overall higher pressure, similar to the behavior of the symmetrical airfoil at a positive angle of attack. In other words, a cambered airfoil will produce lift at zero angle of attack. The more camber an airfoil has, the higher the lift coefficient will be at zero angle of attack. As mentioned earlier, camber can be mimicked by giving the leading and trailing edges of the airfoil a default value and a response to any input, so long as the range values are equal so the edges do not move. In this video, I am using a slider input with variable range so that I may adjust the camber in real time. As I adjust the camber of this airfoil, note that the wing information window displays a very different lift coefficient than that of the flight window. As of version 0.225, the wing's information window only reflects the contribution of the main wing piece to the lift coefficient, and not the leading and trailing edges, while the flight window shows the overall lift coefficient of the aircraft, which is the entire wing in this case. For an airfoil with no control surface deflection, the amount of camber is typically fairly low. In addition to generating more lift at zero angle of attack, high amounts of camber may also increase the maximum lift coefficient of the airfoil. Higher camber airfoils will also generate slightly more drag. In-game, however, increasing the airfoil camber seems to decrease the maximum lift coefficient reachable by the wing, which is opposite to how it should behave. Additionally, it seems the lift vectors don't quite follow the behavior of the displayed lift value in the flight window. During aircraft design, it is useful to express the lift and drag forces that an airfoil generates as if they are resulting at a single point along the airfoil's chord, as shown earlier. To determine where that point is, we first need to review the pitching moment. In addition to lift, airfoils will also generate a pitching moment, where a moment is a torque that is created by a force acting at a distance from some point. As the name implies, the pitching moment will cause the airfoil to pitch upwards or downwards depending on where the moment is taken. In the process of aircraft design, the point at which the airfoil's force system is most convenient to express is at the Aerodynamic Center, which is the point along the airfoil's chord line at which the pitching moment is independent of the angle of attack. What about the center of pressure, you may ask? The center of pressure is the point along the airfoil's chord line at which the pitching moment is zero. For symmetrical airfoils, the aerodynamic center and the center of pressure are both located at the quarter chord, which is the point that is a quarter of the chord length, starting from the leading edge. For cambered airfoils, however, this is not the case. The center of pressure of a cambered airfoil actually shifts as the angle of attack is changed based on the equation on screen. Note the relationship between the center of pressure's location and the lift coefficient. As the lift coefficient increases, the center of pressure shifts towards the leading edge. As the lift coefficient decreases, the center of pressure shifts towards the trailing edge, and further, if the lift coefficient approaches zero, the center of pressure moves towards an infinite distance behind the trailing edge. For this reason, the center of pressure is not very convenient to use. The aerodynamic center, on the other hand, does not move as the angle of attack is changed. Theoretically, it is still located at the quarter chord, however for some airfoils it will not be located directly on the quarter chord, but instead near it, depending on the lift curve slope and the moment curve slope taken about the quarter chord. Typical locations of the aerodynamic center will range from the 22% to 26% point of the airfoil chord. With all of that in mind, the blue sphere in the editor should probably be relabeled to aerodynamic center overlay. Now that we have covered the basics of airfoil lift, we'll take a look at the basics of drag and stalling. Drag on a body can be split into two categories, skin friction drag and pressure drag. There are multiple forms of pressure drag, but for this section of the video, I will only focus on pressure drag due to flow separation. You may be wondering about the terms parasitic drag and induced drag that we saw on the wing information window earlier. Parasitic drag describes drag that is not strongly affected by lift generation and includes skin friction drag and flow separation drag. Parasitic drag can also be referred to as zero lift drag or profile drag. Induced drag actually falls under a category of drag that is strongly affected by lift generation called drag due to lift. Induced drag is a three-dimensional effect that does not apply to airfoils and will be discussed later. Skin friction drag on a body is caused by the presence of a boundary layer, which is defined as a thin viscous region of fluid near said body. Within the boundary layer, the fluid, which is air in this case, becomes slower the closer to the surface it is, where the velocity at the surface is zero, and the velocity far away from the body is equal to the undisturbed free stream airspeed. This boundary layer is the cause of the shear stress and therefore skin friction drag experienced by the body. The amount of skin friction drag at any point on the body also depends on whether the airflow within the boundary layer is laminar or turbulent, where laminar flow is smooth and results in lower shear stress at a given point, and turbulent flow is instead random and irregular and results in higher shear stress. For the incompressible case of flow around an airfoil, pressure drag will only occur if there is flow separation present. Flow separation occurs on an airfoil when the air particles influenced by the airfoil begin to reverse direction, which typically occurs when the air is moving relatively slowly while also experiencing an adverse pressure gradient, which is when air pressure begins to increase along the path of the airflow rather than decrease. This adverse pressure gradient will be experienced past the region where the airflow experiences its highest velocity, but flow will only separate when it lacks the energy to overcome this pressure gradient. The air pressure in the separated region will be lower than that of the attached region, and when this low pressure region is acting on the aft section of the airfoil, there will be an unequal force causing drag. At low to moderate angles of attack, the flow separation will be very small, and most drag will be due to skin friction, but as the angle of attack increases, the region of flow separation will begin to creep towards the leading edge. Near the leading edge, the pressure in the separated region will actually be higher than it would be if it were attached, and lift decreases as a result. This behavior is called stalling. At the trailing edge, the pressure is much lower than it would be if it were attached, and since the trailing edge is steeply angled relative to the airflow, there is also a large increase in drag. For most typical airfoils, one can expect stalling to begin at around 13 to 15 degrees of angle of attack, though the base stalling angle for airfoils in game is about 8 degrees, which is much earlier than it should be. Additionally, there are differences in stalling behavior based on the airfoil's shape that the game unfortunately does not simulate as of version 0.225. I will update a pinned comment should this change in the future. If you want to skip the review of these differences, go to the timestamp on screen. There are 3 basic types of stalling behavior which are affected by the airfoil's thickness. The first is the trailing edge stall, which was previously discussed, where the flow begins to separate at the trailing edge and works its way up to the leading edge. This type of stall exhibits a relatively smooth peak in the lift curve slope and is generally observed in thicker airfoils. Conversely, the second type of stalling behavior is the leading edge stall. This is where the flow separates entirely from the airfoil at the leading edge, leading to a sharper peak in the lift curve slope and a more aggressive stall. The peak lift coefficient will be slightly higher than that of a trailing edge stall, however. This behavior is typically observed in relatively thin airfoils. The third type of stalling behavior is a characteristic of very thin airfoils and can be referred to as a thin airfoil stall. This behavior involves the flow separating from the leading edge but reattaching down the length of the airfoil at low angles of attack. As the angle of attack is increased, this separation bubble becomes larger until it encompasses the entire upper surface. This process results in a smooth stall similar to that of the trailing edge stall, however, the maximum lift coefficient of a thin airfoil stall is much lower. Because of this, very thin airfoils are not very useful at low speed flight, but they are useful for supersonic and low hypersonic flight for reasons that will be discussed in the next wing tutorial video. Note that Flyout's force center shifts back as the wing stalls, even with symmetrical airfoils. Observing data for real symmetrical airfoils, the pitching moment about the Aerodynamic Center does actually decrease significantly during a stall, so this is a reasonable behavior. Even so, the amount and even direction that the pitching moment changes by varies per airfoil, so the distance, and in some cases direction, that it moves in Flyout is not necessarily correct. Returning to airfoil drag, there are no nice and simple approximations to estimate total drag the same way there are for lift. Additionally, the drag coefficient is generally very sensitive to multiple factors, such as whether the flow is separated or attached, turbulent or laminar, and so on and so forth. It is at least possible to obtain a somewhat reasonable estimate for skin friction drag by using equations for that of a flat plate. We can, however, compare data from Flyout for airfoils with varying thickness to that of real airfoil drag polars, where a drag polar is a plot of the drag coefficient per a given lift coefficient. Note that the polars I will show do not include data for stalling. Starting with a very thin airfoil and comparing to a real airfoil of similar thickness, we can see that Flyout's drag coefficients slightly undershoot the real data. Note that the range of values I could obtain was somewhat limited by Flyout's coefficient displays only having 3 decimal places, so this data may not be entirely representative of how the drag polars in Flyout actually look. Moving on to an airfoil with average thickness, we can see that for this airfoil shape, Flyout's airfoil drag at lower lift coefficients is significantly higher than what one might expect. Here are the previous drag polars for comparison. Finally, we can see that the drag puller from real data on a thicker airfoil shows a slight increase in the drag coefficient compared to an airfoil of average thickness. The drag coefficient for a thick airfoil in Flyout, however, is significantly higher than it should be. Note that for real airfoils, the airfoil thickness having only a comparatively small effect on the drag coefficient will not hold at much higher speeds, as we will see in a later video. Here are some more drag pullers for various airfoil shapes in Flyout. Before discussing aerodynamic properties of wings, I will discuss some parts of their geometry that will be relevant moving forward. First, we have the wingspan, denoted by the letter B. This is a measure of the distance between the wingtips. Next are the root and tip chord lengths, which are the chord lengths of the airfoils used at the wing root and tip, respectively. The ratio of the tip chord length to root chord length is the taper ratio, denoted by a lowercase lambda. A taper ratio of 1 means the root and tip chord lengths are equal, and a taper ratio less than 1 means that the tip chord is smaller than the root chord. Next is the wing sweep, denoted by an uppercase lambda, which is a measure of how far back the wing is angled. Wing sweep is commonly measured to the leading edge, quarter chord, or half chord. Certain analyses of the wing can use different chord locations to measure sweep to, some of which will be covered later in this video. Planform area, denoted by capital S, is the geometric area of the wing viewed from above and includes the theoretical wing area that will be enclosed in the fuselage. The planform area can be calculated using either of the two equations on screen, where the first is the more general form that can be used for any wing shape, and the second is for a linear tapered wing. Keep in mind that the planform area is not the same as the wing's total surface area, as it does not include the surface area of both the upper and lower surfaces of the wing. The final basic geometric parameter I will cover is the aspect ratio. The aspect ratio is calculated as the square of the wingspan divided by the planform area and is a measure of the slenderness of the wings. Long and narrow wings will have high aspect ratios, and short and stubby wings will have low aspect ratios. When designing an aircraft, it is important to know where the aerodynamic center lies along the wing so that we may have a rough estimate of the aircraft's longitudinal stability. The aerodynamic center of the wing will lie on its mean aerodynamic chord, which can be found using the equations on the screen, where the first is again a general form, and the second is for a linear tapered wing. The aerodynamic center will lie at the same point along the mean aerodynamic chord as it would on the airfoil at that location of the wing. Recall that for symmetrical airfoils, this will be exactly at the quarter chord of the wing, and for cambered airfoils, this will be at or near the quarter chord point, though using the quarter chord in general is a reasonable approximation. In Flyout's editor, the blue sphere accounts for the aerodynamic center of every wing part on the plane, including angled vertical stabilizers. It does not account for the location at which the game generates lift from fuselage parts, since this location is calculated when the player goes to fly the aircraft. For a reasonably stable aircraft, the aerodynamic center should be behind the center of mass, but not too far. Here are some examples for reference. It is possible to make flyable unstable aircraft, but this will involve the use of fly-by-wire, which will be covered in a future tutorial. Unfortunately, Flyout's calculation of the aerodynamic center location can be largely incorrect depending on how your wing nodes are placed. Not only does this affect the displayed location in the editor, but it also affects the location of the wing force centers in flight. I believe the cause of this involves Flyout's version of blade theory. In other flight simulators that use blade theory such as X-Plane, a wing is divided into multiple smaller segments, or blades, and the aerodynamics of each element are calculated individually. Each element also has its own aerodynamic center, rather than having one singular aerodynamic center defined for the whole wing. Flyout takes a similar approach, but differs in that the elements can be shaped such that their edges are not purely chordwise. I believe this causes their aerodynamic calculations to go awry, which causes the discrepancy shown earlier between two wings that should behave identically. One other thing to note about Flyout's aerodynamic center display is that it does not account for the theoretical wing area that would be enclosed in the fuselage, but this is somewhat of a blessing in disguise, as a real wing section would not be generating lift while being enclosed inside of a fuselage. Now that we are analyzing a finite wing instead of an airfoil, we can calculate the actual amount of lift and drag generated by the wing rather than the lift and drag per unit span. To do this, we need the wing's lift and drag coefficients and the wing's planform area. Note the difference between the notation for the finite wing's force coefficients and those of an airfoil, where a finite wing's coefficients use a capital letter and those of an airfoil use a lowercase letter, as the coefficient values will actually be different. The reasons behind this will be explained in the next section of the video. Recall that the planform area includes the theoretical wing area between the actual wing roots and the fuselage instead of just the exposed or wetted wing area. Flyout actually does calculate this theoretical wing area based on your wing placement when you launch your aircraft. Note that the wing area in the editor stats window only includes the area of the actual wing parts and not the theoretical wing area. Another thing to consider regarding reference areas is that the reference area used when obtaining coefficient data on real aircraft is often only the planform area of the main wing, not including additions such as strakes. In Flyout, the reference area includes the horizontal area of all wing parts, including additions, though it can also use fuselage area instead if there are no wings present. The distinction between the reference area in Flyout versus real aircraft design is important to consider if you are trying to compare your aircraft's performance to that of a real aircraft, as it will affect the lift and drag coefficients displayed in the flight window. This does not affect the actual performance of the aircraft, however, as the flight window's lift and drag coefficients are calculated using the lift and drag forces that every part on the aircraft generates instead of the other way around. There is currently a bug where the reference area will be different depending on whether or not your leading and trailing edge surfaces have inputs assigned to them. Without inputs, the reference area will be much larger than the actual planform area. Unfortunately, this also affects the game's calculation of the effective aspect ratio of the wing, where the aspect ratio is much lower without inputs assigned compared to with inputs assigned. The effects of the aspect ratio on flight performance will be discussed shortly. Now that we are working with finite wings, there is an important phenomenon that we will need to deal with when designing and flying aircraft. This phenomenon is the wingtip vortex. Wingtip vortices are generated when the high-pressure air on the lower surface of the wing moves to the low-pressure zone on the upper surface of the wing by flowing around the wingtip. Two side effects of wingtip vortices are downwash of the air around the wing and induced drag. Downwash on the wing is a result of the downwards motion of the vortices causing a slight downward local velocity at the wing section. This in turn causes the effective angle of attack to be reduced from the geometric angle of attack, where the geometric angle of attack is the measured angle between the free stream air and the wing section's chord line. This reduced effective angle of attack causes a decrease in lift. The resulting pressure distribution of the airflow with wingtip vortices also creates a component of drag, which is referred to as induced drag. Factoring in induced drag, the total drag coefficient of the wing becomes the equation on screen. The first term is the drag coefficient of the airfoil at a certain lift coefficient, and the second term is the induced drag coefficient. Notice that the induced drag is heavily dependent on the wing's lift coefficient and the aspect ratio of the wing. The dependence on the aspect ratio is actually misleading, as redimensionalizing this equation by multiplying it by the dynamic pressure and planform area shows that the induced drag is actually dependent on the square of the wingspan. However, if the wing area is kept constant while changing the wingspan, then it is not unreasonable to state that the aspect ratio has an effect on induced drag. With that said, we can see that a higher lift coefficient will generate significantly more induced drag, and a higher aspect ratio wing will generate less induced drag. You may also be wondering about the lowercase e in the denominator of the induced drag term. That is the span efficiency factor of the wing and is a function of the wing's aspect ratio and taper ratio. This is not to be confused with the Oswald efficiency factor, which is used in a very similar looking equation for the drag coefficient of a complete airplane as shown on screen now. Let's return to the span efficiency factor. The span efficiency factor is determined by the wing's efficiency at generating lift, which is most efficient when the lift generation along the wingspan is elliptical. Elliptical lift generation offers a constant downwash and thus a constant induced angle of attack along the wingspan, yielding the lowest possible amount of induced drag. The value for the span efficiency factor with elliptical lift generation is 1. For a wing to create this perfect elliptical lift, it must be shaped elliptically as well. Although elliptical wings are the most efficient in lift generation, they are also complex and expensive to manufacture when compared to wings with straight edges. A commonly used compromise is to taper the wings to provide a lift generation that is closer to elliptical than that of a rectangular wing, which is suboptimal. At the time of writing, the taper ratio does not seem to have an effect on wing efficiency in Flyout, although some form of lift distribution is modeled such that the root of a rectangular wing generates more lift than the outboard sections. Because of this, one should be mindful when making certain control setups, such as twin boom aircraft with a central wing as the horizontal stabilizer. Just using one wing part will have an uneven lift distribution and will roll slightly as a result. It is recommended to use two mirrored wing parts instead. Because wingtip vortices cause downwash on the wing, and the aspect ratio affects the prominence of this effect, the aspect ratio will also directly affect the lift curve slope of the wing. A smaller aspect ratio will lead to more downwash over more of the wing, which will lower the lift curve slope, meaning that a higher angle of attack is required to generate an equivalent lift coefficient compared to a higher aspect ratio wing, but this also has a beneficial effect in that the stall angle is also increased. Note that the greater downwash also lowers the maximum lift coefficient obtainable by a wing with a lower aspect ratio. The opposite is true for high aspect ratio wings, which will have a steeper lift curve but will stall earlier than a low aspect ratio wing. Observing this graph made with data from Flyout, we can see that the game models this behavior fairly well, up until the aspect ratio starts to become very high, where the issues with the airfoil curve become prevalent, namely the steepness of the lift curve and the fact that the maximum lift coefficient starts to decrease, which should not happen. The issue with the steepness of the lift curve will be discussed after a quick note on asymmetrical wing stalling. If one wingtip stalls before the other, the difference in lift will cause a rolling moment. This is referred to as wingtip stalling. This rolling moment will be much stronger the longer the wingspan is, and it will be more violent for higher aspect ratio wings. Returning to the issue with the in-game lift curves, there is an empirical equation that can help estimate the lift curve slope for tapered wings, given the aspect ratio, Mach number, and some other parts of the wing's geometry. Note that this approximation is only valid for subsonic speeds, even those above Mach 0.3, but only below the wing's critical Mach number, which will be covered in a later tutorial. Note that this equation is only for simple, tapered wings rather than a more general, complex shape. This graph plots the slope of the lift curve with respect to the aspect ratio of the wing. The smooth, curved line is from the previously mentioned equation. As the aspect ratio tends towards infinity, it reaches a limit equal to 2 pi, which is the thin airfoil theory lift curve slope. The points above the equation curve are results from testing untapered, unswept wings in Flyout. As we can see, the lift curve slope in Flyout is significantly higher than the equation results, which means that for a given angle of attack, most wing configurations will have a higher lift coefficient than they should. We can also extrapolate that they stall earlier than one would expect, which is much more prominent for high aspect ratio wings. It's also worth noting that the game currently has a minimum effective aspect ratio of 2. Next, I will cover the effects of wing sweep on a wing's lifting and stalling properties. These are not currently modeled in-game, but are still good to be aware of. There is a minor difference in lift if one simply rotates the wing part and matches the shape for a normally swept wing, but it is nowhere near the expected behavior. A simplified look at sweep effects on lift is provided by simple sweep theory. When a wing is swept, the flow over an airfoil section of the wing is split into components parallel and perpendicular to the leading edge. The perpendicular flow component will have a lower velocity compared to the streamwise flow velocity, which lowers the amount of lift generated per a given angle of attack compared to an unswept wing. The sectional lift coefficient will be lowered by the cosine of the leading edge sweep for small angles of attack. Unfortunately, simple sweep theory is only applicable to a wing with infinite span and no taper in an inviscid fluid flow. This means that it does not allow for predictions for effects on the drag or maximum lift coefficient that the wing can reach, since these rely on viscous effects, and it may not be accurate for finite tapered wings. It will, however, make another appearance in the next wing tutorial when transonic flight is discussed. The empirical equation from earlier can be used here to help approximate the lift curve slope for a finite swept wing using the half-chord sweep, but this once again falls short for wings that are more complex. Regarding lift distribution, an aft-swept wing will experience a bias in lift towards its wingtips due to the wing experiencing less downwash on its outboard sections compared to its inboard sections, which will experience more downwash. This will cause the lift distribution to diverge greatly from the ideal elliptical lift distribution and will result in additional induced drag. Washout, which will be explained later, or a taper ratio can be used to alleviate this effect. The use of taper does not come without its risks, however, as will be discussed shortly. Now is a good time to discuss stall progression on certain wing shapes. Starting with a rectangular wing and recalling its downwash distribution, we can see that the inboard sections will experience the highest angles of attack and will stall first, while the outboard sections stall later. For the case of the elliptical wing, recall that the downwash is constant across the wingspan, leading to the entire wing experiencing a constant angle of attack. As the wing stalls, the wing will stall across its span simultaneously rather than at the root or tip first. Since a moderately tapered wing is often used to mimic an elliptical wing's lift distribution, we can extrapolate that a moderately tapered wing will experience a similar stall progression to that of an elliptical wing. For both swept wings and highly tapered wings, the wingtip will experience a higher angle of attack compared to the root due to the decreased downwash at these locations as discussed previously. This will result in the outer sections of the wing stalling before the rest of the wing. According to Daniel Raymer, an expert in aircraft conceptual design, the taper ratio should not go below 0.2 except for delta wings as to lower the risk of wingtip stalling associated with taper. Delta wings are a special case that will be discussed in the next section. Aft-swept wings also have a reputation of stalling at the wingtips earlier because of air in the boundary layer moving towards the wingtips, but according to McLean, this problem is often overstated since air in the boundary layer can only migrate long distances when flow separation has already begun. A forward-swept wing will experience a downwash distribution opposite to that of the aft-swept wing, such that the root experiences less downwash and the wingtip experiences more downwash, leading to the root stalling first. Unfortunately, reverse-swept wings are not always practical due to the aerodynamic and structural instabilities they can induce, often requiring the use of fly-by-wire and advanced materials or a reinforced structure. Stall progression for various wing shapes is not currently modeled in-game, as all wing sections at equal geometric angles of attack stall simultaneously. Next, we will discuss delta wings. Given the previous discussion regarding wing sweep lowering the lift curve slope and increasing the prevalence of wingtip stalling, one might expect delta wings to have very poor performance qualities, as delta wings are typically highly swept compared to regular swept wings. When at a positive angle of attack, a delta wing with sharp leading edges will produce a set of vortices over the upper surface of its leading edge. These leading edge vortices are a result of flow separation at the leading edge due to the sharp corner. The static pressure in these vortices is low, which causes the pressure over the upper surface of the wing to be lower near the leading edges, while the middle section is also relatively low. This results in an extra lift contribution by the leading edge vortices known as Vortex lift. The presence of these vortices allows for the air to remain attached to the wing at higher angles of attack than it would without them, allowing for delta wings to achieve very high angles of attack without stalling. One drawback delta wings face is that their lift curves are quite shallow compared to more conventional wings, although this should be no surprise considering their typically low aspect ratio. The drawback of vortex lift is that although significant lift is generated by these vortices when at higher angles of attack will mean that the normal force the surface experiences is tilted aft, causing significant drag. As a result, lift-to-drag ratios of delta wings at lower airspeeds is often poor. One way to mitigate this is by making the leading edges less sharp to reduce or eliminate the flow separation that generates the vortices, which will significantly increase the lift-to-drag ratio, but may also reduce the vortex lifting capabilities. This can also have adverse effects on supersonic flight. This will be discussed more in a later video. Delta wings are also not the only surfaces that can experience vortex lift. Any highly swept surface with a sufficiently sharp leading edge at an angle of attack is capable of generating a vortex. Vortex lift on wing parts is not currently modeled in Flyout, so delta wings and features such as sharp strakes will behave as regular wings. There is still a benefit to adding these features to your aircraft if you are looking to increase your stall angle, as the extra surface area will contribute to a lower aspect ratio so long as they are part of the main wing. The lurks part, however, does actually appear to have vortex lift modeled to some extent, though it still is different from what one should expect. One unique characteristic of a surface producing vortex lift is the nonlinear nature of the lift curve. To Flyout's credit, this part of the lift curve appears to be modeled fairly well. Additionally, a longer, more blade-like lurks part will give a steeper lift curve and also more drag, which is expected. Although the shape of the lift curve is correct, the sleeker lurks part should be able to reach a higher maximum lift coefficient and stall angle than that of a regular wing part, but in Flyout both lurks parts stall at roughly the same time as the regular wing parts tested, which had aspect ratios of 2. The sweep angle should also affect the maximum lift coefficient and stall angle. Additionally, adding lurks parts to your wing will not increase their stall angle. To avoid going down a rabbit hole about vortex lift in this video, I will recommend checking out the vortex lift related sources in the description if you wish to see how different sweep angles and shapes affect lift and drag for delta wings, as discussing the topic is worthy of a separate video entirely. Next, I will cover ways to delay stalling and high lift devices. The first way to delay stalling in Flyout is simply to decrease the wing's aspect ratio as mentioned earlier, but this will also result in increased induced drag, which may be undesired. Before discussing other stall delay methods, note that I will be measuring the angle of attack relative to the chord line as if the leading and trailing edges are not deflected, even if they are. The source I am following does the same thing, so this is important to remember when comparing in-game results to real data. The second method is to add an alpha response to the leading edge and configure it so that the leading edge only deflects downwards. This results in a device known as a droop flap, which is a type of leading edge flap. Droop flaps will increase the camber at the leading edge, and the increased curvature at the leading edge helps delay stalling as a result of a reduced peak in pressure at high angles of attack. Because the chord line of the airfoil is also angled downwards, the airfoil's effective angle of attack is lowered, causing a decrease in lift at a given angle of attack using the measurement convention mentioned earlier. In Flyout, droop flaps only seem to lower lift at higher angles of attack when the entire lift curve should be shifted right instead of just the later part of it. Additionally, the maximum lift coefficient is lowered when it should increase. The stall angle should also be increased more. Keep in mind that I only tested a 15-degree deflection, and results may differ for lower or higher deflection values and different flap sizes. Keep in mind that this is a leading edge flap, which is not the same as a leading edge slat. A slat typically has the leading edge of the airfoil move forwards and downwards, which, in addition to having the same purpose as a regular leading edge flap, also serves to increase the wing planform area and direct some of the high pressure air from the lower side of the airfoil to flow over the upper surface of the airfoil, delaying flow separation and increasing the stall angle and maximum lift coefficient significantly. Unfortunately, slats cannot be created accurately in Flyout at the moment. Another method is to add an alpha response to the trailing edge of the airfoil so that it deflects upwards. This is also referred to as reflex, though this term can also be applied to an airfoil shape with the trailing edge deflected upwards without any control responses. Similar to the leading edge flap in Flyout, this reduces the angle of attack of the airfoil by angling the chord line downwards. Opposite to the leading edge flap, however, this inverts the airfoil's camber near the trailing edge, resulting in less lift. As such, it is advised to only use reflex near the wingtips as to not lower the lift generated by the wing by too much. Reflex does not increase the actual stall angle of the wing in Flyout. It should be noted that in reality, reflexing the trailing edge upwards will not help delay the wing section from stalling for airfoils susceptible to leading edge stalls or thin airfoil stalls, as the entire upper surface will already be enveloped in the separated flow region as soon as the wing stalls. The next method is to twist the wingtip so that the leading edge is angled downwards slightly. Similarly to a leading edge flap, this reduces the angle of attack of the wing section that is twisted, but passively rather than actively. Twisting the wingtip downwards in this manner is effective at delaying wingtip stalling, but it can also result in less efficient lift generation when flying normally depending on your wing configuration. Note that twisting the wingtip with the leading edge downwards is also referred to as geometric washout or just washout. The last stall delay methods I will discuss do not actually work in Flyout, though they are still good to keep in mind. The first of these is the dog tooth, also referred to as a snag or notch. This consists of the leading edge of an outboard wing section being extended forward slightly compared to the adjacent inboard section. This creates a vortex that forms over the upper surface of the wing at the location of the dog tooth, which helps delay a stall from spreading to the unstalled section of the wing. In Flyout, adding a dog tooth to your wing will have a small effect on delaying a stall, but only because the aspect ratio of the wing is decreased due to the slight increase in wing area, assuming the chord of the dogtooth section is greater than it would be without it. The next method is to use sets of vortex generators. Vortex generators are small plates that are angled relative to the airflow, which creates vortices near the surface they are placed on. This keeps the airflow attached to the surface at conditions where it would normally separate up to a point. The last of these methods is the wing fence. This serves the exact same purpose as the dogtooth, but instead of a vortex, it utilizes a physical barrier to separate stalled and unstalled sections of the wing. Moving to our final high lift device, we have the plane flap. A plane flap increases lift by deflecting the trailing edge of the airfoil downwards to increase the airfoil's camber. One thing to keep in mind with plane flaps is that as the flap's deflection angle reaches higher values, the flow over the upper surface will begin to separate, causing the airfoil to begin stalling. The larger the flap is, the more this will affect the airfoil's performance. Although the flow separating over the flap surface can be detrimental to lift, it can also be taken advantage of in the sense that drag will also be significantly increased, which can greatly help to slow an aircraft down when landing. Here is a comparison of lift coefficients for a real airfoil with flaps retracted versus deployed 15 degrees. Note that this airfoil is already cambered without the flap deployed, so the lift curve is offset to the left slightly to begin with. When plane flaps are deployed, the increase in camber will raise the maximum lift coefficient of the airfoil and also offset the lift curve to the left. Additionally, the issue with flow separation near the trailing edge at higher angles of attack causes the stall angle of the flapped airfoil to be decreased. In Flyout, however, we see a very different behavior. For low amounts of flap deflection, the maximum lift coefficient is not increased, nor is the stall angle decreased. At lower angles of attack, the lift curve is offset to the left, but this does not persist at higher angles of attack due to the slope becoming shallower for some reason. At higher flap deflection angles, the behavior does actually become somewhat correct, though it still shows a shallower lift curve, and the maximum lift coefficient is nowhere near as high as it should be. For comparison, here is the data from the real flapped airfoil overlaid on the same graph. Note that the 40-degree deflection for the real airfoil has been added. There are other types of flaps in high lift devices such as split flaps, and slotted Fowler flaps that help remedy the flow separation issue that plane flaps have, but they are unfortunately not currently available in Flyout. Deploying flaps will also cause a downwards pitching moment on the airfoil, though whether or not your aircraft pitches down with flaps deployed depends much more on the location of your wings relative to the center of mass. Placing the wings too far ahead of or behind the center of mass will cause a significant upwards or downwards pitching moment, respectively. The final topic I will be covering for this video is ground effect. As the name implies, ground effect occurs when an aircraft's wing is close to the ground relative to its wingspan. Once the wing becomes affected, one can expect an increase in lift and a decrease in induced drag. One explanation of how ground effect works is that the presence of the ground obstructs vertically moving air, reducing downwash on the wing. Recall that the downwash on a wing causes induced drag and a decrease in the effective angle of attack. With this in mind, the reduced downwash will essentially cause the wing to behave as if it has a higher aspect ratio, reducing induced drag and increasing the steepness of the lift curve. Because there is less downwash, this also means that the stall angle of the wing will decrease. A commonly used estimate of the distance from the ground for ground effect to affect the wing is half of the wingspan, which is reasonable, although we will shortly see that it actually begins taking effect at a larger distance than this. The explanation just given is the three-dimensional component of ground effect. The two-dimensional component of ground effect, which pertains to airfoils instead of finite wings, actually sees the airfoil lift decrease due to the increased pressure on the upper surface until getting fairly close to the ground, at which point it will begin to increase slightly due to a pressure increase on both the upper and lower surfaces, with the lower surface seeing a larger increase. McLean also says that the widespread notion that there is a cushion of air under the airfoil is not a bad one, but that the pressure increase on both surfaces and not just the lower one should be kept in mind. He later goes on to state that the three-dimensional component of ground effect is typically the dominant one, as the two-dimensional effects require the wing to get closer to the ground than would normally be of practical interest. For ground effect vehicles whose wings are typically very close to the ground, however, the two-dimensional effects will likely remain relevant. Flyout does have ground effect modeled. First, I will compare lift ratios of a rectangular wing with an aspect ratio of 10 in Flyout to those obtained in a lifting line calculation provided by McLean. The wing in both cases is kept at a fixed angle of attack such that the initial lift coefficient is 0.81. As we can see, Flyout initiates ground effect at half the wingspan. This is a reasonable starting point, though the effects past that are not insignificant. As the wing gets closer to the ground in Flyout, it briefly overshoots the lift increase provided by the lifting line calculation, and then plateaus afterwards at a lift ratio lower than expected. Regarding the effective aspect ratio part of ground effect, Flyout does seem to take this into account, and it does so fairly well, though the issues with the airfoil lift curve become very prevalent as seen by the decrease in maximum lift coefficient as the effective aspect ratio increases, when instead the maximum lift coefficient should increase due to the decreased downwash. For drag, however, it seems that the wing in 100% ground effect does not quite conform to the game's airfoil values one would expect, as incorrect as the airfoil behavior may be. This may be related to the wing readout issue I pointed out earlier in this chapter, where the drag percentage in the wing's info window shows an increase in induced drag rather than a decrease, but I cannot say for sure without having read the game's code. To end the video, I will begin by saying that as far as aerodynamics models go, Flyout probably has the best one out of any vehicle building game that I've played. As we've seen, however, it is not without issues for a model that attempts to be reasonably realistic. As far as possible improvements go, here's a list of improvements that I believe will be possible in the game, with varying degrees of difficulty based on how I believe the game works without knowing how it is programmed. Some of these may be minor changes, while others could require significant effort or even rewrites to the wing model. It may be worth making a video going over how all these could be implemented, but I will likely wait till after I complete part 2 of the wing tutorial to do that. I would also like to reiterate that this video was focused on exploring aerodynamics of wings in the incompressible flight regime where airspeeds do not exceed Mach 0.3. The next wing tutorial will focus on speeds higher than this, including transonic, supersonic, and hypersonic speeds, and most likely will be much shorter than this video was. I also didn't speak of stability effects of certain wing shapes or control surface movements, as stability and control topics are more fit for their own tutorials that I will cover later. The same can be said for things like specific tail shapes, canards, wingtip devices, and so on and so forth. With that said, I will probably try to make 1 or 2 non-wing tutorials before working on Wings Part 2, with a follow-up to turbine engines being a likely candidate.